performance easy. Yeah. Hi, and welcome everybody to the High Performance Easy Gains of Simple CUDA tutorial. My name is Bernhard Raml. I'm from the TU Wien, and I'm at the TU department, and I work together on the C-Scale project as a researcher. And I've been on the GPAD use case where we investigated GPU devices for our high-resolution remote sensing data. My background and why I feel somewhat qualified to talk about CUDA and GPUs is actually from gaming. So I've been a games developer for 5 years before I went into industrial inspection and research, where we do high-performance computer vision, also GPUs in factories, finding defects and things like that. Before I came here, where I'm now processing mostly Sentinel-1 microwave radar data at the 10-meter, 20-meter scale. It's a lot of data, very high resolution. And for many of our, turns out, for many of our algorithms are well suited for GPU devices. So before we start into the specifics on GPUs and CUDA, I want to talk briefly about how to write high-performance software in general. So why do I do this? And the thing is, the GPU, what I'm trying to do is here with this tutorial is kind of give you, dispel a bit the magic of the CUDA GPU black box and kind of give you a bit background why this thing is well suited for certain tasks and how it actually works. Also on a hardware level, I'll be very brief though on the hardware side. And so you have a better understanding and can hopefully then kind of decide yourself that for which types of problems this might be the right tool. And because there's lots of tutorials online, like teach me CUDA in 10 minutes and things like that that get you the basics. But I want to fill this gap between, a little more in-depth knowledge about the mechanics behind the scene and the actual application, in our case, to real Earth observation tasks, as an example, but is probably true for many other tasks. Yes, so at the core, even on CUDA, whatever you do, these principles I'm going to talk about, they are just, doesn't matter what you use, they are just, even if you do CPUs or field programmable arrays, it's usually on a high level the same. So here, one of the most important things is, and I can't stress this enough, is that habitability of the code base comes before speed. Why do I say this? What do I mean with habitability? Let's start with that. So a good habitable code base means you have automated tests in place that you can make changes to your source code confidently without fear of breaking anything. So that also means, because it brings me to the point of, if you write high-performance software, usually you have this 80-20 rule there, like 80% of the time of your code is spent in 20% of your code. And if you have a nice design, a maintainable code base where you can easily change things, you can make those 20% more high-performant much more easily than if you have less habitable code base where you are afraid to make any changes, or where you need to look for very long to find those 20%. So there's no way around, I think, around habitable or clean code, even for high-performance software. I know there's been an argument online from someone from the game dev scene, since I'm myself a former game dev who knows where this person is coming from. And he says, like, you have to, that maintainability and habitability has performance costs, and you should worry about those as well. That is true, but however, to be honest, it always depends on your context. That's another very important lesson for high-performance software, even when deciding to use GPUs or CPUs, is, does it make sense for what I'm doing? Like, is the speed up really worth it? And where do I spend my time, my runtime? And this is also why measuring, which is going to be the next topic, is so important. Because if I spend most of my time decompressing my data, it doesn't matter if I use a GPU to do the processing or add more CPUs to my node. I'm still gonna do spending time reading stuff from the disk. So changing the right things is very important. That also gets you the most benefit. So here a little story, just to give this a little bit more more context to make it a bit more concrete. So for a project I've been working on recently, I had to create a lookup table for a really high resolution raster data. It took really long, like half an hour. And I thought like to myself, well, yeah, half an hour. 2D tree is slow, creating spatial index is slow. If half an hour, it's fine. So it's the 2D tree is slow, right? Wrong. I actually followed my own advice. I didn't follow it for quite a long time until I had enough. And then I followed it and I started actually profiling. In this case, I use what you see here is PySpy, Python sampling profiler, and measured how long the resampling actually took. This is actually from an open source package called PyResample. And this is an excellent example for a habitable code base because they have a very high automated test coverage. It was very easy for me to find the actual problem. So what is the problem? The problem is here. Most of the time, I don't spend any time in creating the spatial index. This is over here, like this squeezed to the right part. Most of the time I spend in VStack, which most of the time spends concatenating arrays. And then when I looked into the code, I saw that they would stack numpy append to this lookup table because they have to feed it in chunks because the lookup table is really large, so it doesn't fit into memory. So they calculate parts of it and then concatenate that at the end together. But concatenation takes really long with numpy concatenate because at the end you have a very large array, gigabytes long, that you need to make a complete copy with some additional slice at the end where you put the new slice in and then have to copy the whole thing again for the next slice. It gets really, really slow. People who have experience with C probably already have standing hairs on the back and they hear something like that. And usually in C, for instance, you have things like std vector, which always double the size if they're full. So instead of only allocating extra space for the little slice that comes at the end, they allocate twice the size. But I'm getting carried away. So I just changed some code. I started pre-allocating the whole memory array, and lo and behold, this is how it looked like then. Then it was actually this query sample QD tree get neighboring info. So the QD tree was actually then the bottleneck, and the whole thing, instead of taking 30 minutes, you can see over here, only took about 4 minutes, which is a magnitude of speed up just by pre-allocating the array. And the people at PyTroll and PyResample are really nice actually, so I could quite quickly send out a pull request with my change, and we had some discussions, and it should be in then with the next release. So if you use PyResample for high resolution data, maybe your lookup tables get faster as well. But why this long rant about the story? And it just should show you how important it is to measure, and your intuition at first, even if you had a lot of experience, usually wrong. Mine is, maybe I don't have that one, maybe someone with much more experience than you can probably have the right intuitions, but in general, I would say always measure before you act. Yeah, this is one of the most important things. And now we get to the core of one of the techniques and how to actually, once we have found what slows us down, there are some patterns that always occur that speed things up. And well, I already showed you pre-allocation is a classic. Then there's caching. Instead of recalculating everything all the time, you cache whatever you calculated and reuse it. But one of the most important things, especially now we're getting into GPU territory, is streaming, because this is kind of the trick how you increase the throughput. So we quickly have to talk about latency versus throughput. So for instance, if a low latency and low throughput channel would be, for instance, high priority airmail. So you can send stuff all across the globe very fast, but not a lot. And it's very expensive. However, an example for high latency and high throughput would be a container ship. You can send around like tons of stuff, relatively cheap, but each container itself is really slow, but the flow of material is really large compared to airmail. And so, and what of the two you want is actually context dependent. So we're back again, you need to measure to find out what is actually holding you up and what is what you want. So, but GPUs are really good for things that require a large throughput. They are optimized towards throughput. This is why I'm talking so much about it. And the way you usually achieve higher throughput is by streaming. So streaming means similar how YouTube and Netflix does it. So when you watch a YouTube video or a Netflix video or whatever, you see that it usually starts with buffering. And what that means is it's prefetching some data. And while you're watching, it gives you this smooth experience. It already starts fetching the next chunk of data and the next chunk of data. So until the end of the whole movie, you never experience any hiccups. And this is actually this is the same concept on a GPU or in high performance computing in general. You have a process where you fetch some data. Maybe this is on the disk, which means it's slow and it can only use one CPU, or it's compressed, it needs to be decompressed. And then you do something with it, you process it with all your cores, with your GPU, and then you fetch the next data. But what you can also do is, and to increase your throughput, is you sacrifice a little bit of your memory and you fetch the first chunk, and then you start processing the first chunk. While you're processing the first chunk, you already fetch the next chunk. It's also called I/O hiding, latency hiding. It has many names in performance computing, but it's one of the core tricks of the trade. And it's also the core thing that makes GPUs so powerful. So now, I already mentioned that GPUs are really good for throughput, whereas CPUs are very low latency. So CPUs can do actually more complex tasks. So for instance, if we look at some classical tasks that if you want to solve with a GPU, first think of which category they fall in and if it's the right tool. For instance, a CPU is really good at complex control flow, which means if you have, speaking in clear English, means if you have a lot of branching or if branches in your code or in your algorithm, a CPU is probably better. So examples for this is the tree or graph search or space matrix operation, as opposed if you have like very, let's call it an embarrassingly parallel task, just lots of simple calculations which are more or less independent from each other and don't branch or do anything. Like for instance, if you multiply dense matrices together or large dense matrices together, it's more suited to a GPU task. Similar again, because CPUs are low latency and optimized that a single core is really fast, they are much better for serial processes, which is I/O or reading from the disk is naturally serial. And compression as well. If you need to decompress or compress something, unless you chunk these into compression chunks, again, it's usually only one CPU core that can do that. Whereas on the opposite, on a GPU, if you have something with really high memory throughput, like video processing or 3D rendering, where actually the GPUs or the name graphical processing unit comes from, it actually comes from the games industry. We pushed the technique a lot back in the days. And I would also argue it's really well suited for many high resolution remote sensing tasks. Yeah, and also at the end, there is a CPU is of course better for general purpose tasks like running an operating system or a web service and things like that, whereas a GPU has some very special chips on board as well to do ray tracing, to do video codecs, but I won't go into detail for this topic because it would get quite extensive. So here we have two examples from Earth observation, or what you usually do in remote sensing. You have on the left a very CPU suited task would be the Canadian tree query, because, okay, let's say I want to find the point on the top left. I look at, ask my query, okay, are you left or right? It's in the left cell, then you go left, and then you're asking, are you on the top or the bottom? Now I'm on the top. And then again, left or right, I'm on the left. So there's many branches that I'm never actually looking into and that I'm executing, which means that a CPU is much more suited to this, because it can do this out of order execution. It can do this. It can execute many instructions on a single core at the same time, which is it's also called SIMD, which means single instruction, multiple data, and speculative execution, which means it thinks it knows which branch the code usually takes and already does some optimizations. Whereas on the right, you see a typical embarrassing parallel task. For instance, if you work with radar data that you have in decibel and you want to transform them into linear units on a huge raster, each of the pixels value in this transformation is not dependent in any ways on their neighbors or anything. You just need to take the value and calculate an exponent of it. And this can do 4 processes, 120 processes can do this in parallel without interruption or without needing to communicate with each other. So this would be a perfect task for a GPU. Yeah, there's also a specialized part I already mentioned, and GPUs for these particular tasks can be more energy efficient as well. So what you want to do is you want to use a CPU if you want to maximize the instructions per cycle, and if they have like a low latency. I think I already talked about most of those things, so we're quickly gonna skip over. Yeah, I think that's too much detail anyways. So I want to leave you just with this analogy. So if your task looks more like on the left of a handmade pasta, which can be very complex, that you make for yourself or your family, specific, tailored to their tastes, then this is probably this is more or less the CPU task. And the GPU task is if you would need to feed thousands of people in a cantina, and they just produce. You can't pick everyone's taste anyways, so it would be quite inefficient to hire hundreds of chefs to do the perfect pasta. It's usually then better to get the factory-made ones. And also, like in the real life, also in software engineering, usually it's a combination of the two, because most people at home might make their own pasta dish, but they buy the factory-made noodles and then do their own twist on it, which is also what they do in software engineering. Usually you have parts that you do on the CPU, where you put in your own flavor, and you have used the GPU to do the throughput heavy lifting in the back. That's usually, most cases, very a combination of the two. So if you remember nothing else from these talks, remember that the CPU is the complex task, and GPU as a homemade pasta. GPU is factory-made, high throughput, lots of noodles, but they look all the same. So let's have a quick look into the hardware. So how does this all achieve? Is this all achieved? This is actually an image from the CUDA programming guide, which I can highly recommend to read, because it's actually quite an easy read and quite well done to understand how the thing actually works. I think I see something in the chat.
Yeah, but comments only comments to your notes. No questions so far.
Yeah, so the CPU is like you see, it's where the hardware reflects the complexity. Like you have each core has its own control unit, its own, and has a very deep cache hierarchy with which it can actually do this low latency performance. It can actually achieve the low latency and all those complex instructions. Whereas on the right, the GPU, and you can see is it only has 2 levels of caches. And actually all those cores on the right, and those are not even single cores, they are core blocks, or warps of 32 threads each, and each of them share an L1 cache in the control unit. And one of these is usually called a streaming multiprocessor on the hardware of a CUDA hardware at least, or an NVIDIA hardware. And multiple streaming multiprocessors then make up the whole GPU. And usually what you do is you define your operation of like on a grid of threads and in CUDA, and then these get distributed to each of those blocks and executed all in parallel. So there's very simple things that are getting executed in parallel. Whereas on here you only have 4 or maybe 16 on your machine, but each of them can do very complex things. Ooh, almost there in the coding session. Am I in time? Yeah. So this one, I thought this is a metaphor which I stole from Dave Farley's YouTube channel, which is also in the links at the end of the presentation. I find it really instructive because a cycle is in a sub-nanosecond region, and people find it really hard to understand, to imagine what this actually means and why it's not the GPU fast and why do I have all those caches. It's because if I can access the hardware fast, I can of course do my processing also fast. And if I have another level of cache, then I can stream the data from the slower cache into the faster cache. So I can do the fast thing and get the next thing already, which I know will already take longer, and I can make hierarchies of those streaming processes. And depending on how many of the fast, if I have more fast things than slow things, I get more throughput. I can work more workers that query the larger caches or larger memory banks. I can get more throughput. So usually in this metaphor, it means if a thread accessing, usually the threads are organized in warps, which are 32 threads each, and each thread has its own register, which are then grouped into blocks, and each block, which has 512, can have maximum 512 or more threads. Each block then has some shared memory, and these blocks are then again grouped into streaming multiprocessors, and those streaming multiprocessors are the largest unit, and which are then used to distribute work across the GPU. So if for instance, a thread has to ask its register, if we say like 1 cycle equals 1 second, it takes a second. If it has to talk to the shared memory within its block and share information within the threads, it's 2 to 4 seconds. Whereas on the left, the purple thing here again, the L1 cache, it already can take up to half a minute. Whereas if I have to ask the L2 cache, the level 2 cache, I can have to wait a minute. And when I have to, the data is not in one of the caches, I have to load it actually from the device memory. This I can wait up to 10 minutes. So this is like very long idle time in case the data I want is not in the cache, which can explain why very often the performance improvements are on the orders of magnitudes. And if the thing I'm looking for is not even on the device, on the GPU itself, but I have to load it from the normal RAM, it can take hours. And yeah, so from a, if I would, how would this be if I would have to load stuff from a hard disk? And if anyone wants to chime in this metaphor, would it be days, weeks, months?
I'll say days only.
No, it's actually a spinning Rust hard disk, not an SSD, would be months even, and accessing stuff via the internet, like assuming a long distance connection, will take years in this metaphor.
Oh my God.
It's mind-boggling. So now I'm done with my theory lessons. I hope you enjoyed it and I didn't bore you too much, and we'll go into the coding session. I need to remember my password. That was close. Yeah, if there are any questions, please feel free to interrupt me and ask them. Since everyone's fresh to CUDA, I might quickly do the little hello world before we get into the. Because we had someone who wanted to look at profiling tools. So first we're gonna look at the problem. So I have this Gaussian blur code. Very often I have to do. It's also in remote sensing, this can happen that you have to do some Gaussian filtering or some coarsening. And this one is nice because it has a nice overlap with computer vision and with computer graphics, and this is already well researched, and it's easy for everyone to find tutorials for this CUDA because it's such a traditional application of a GPU. I will share the repo with you later on. You will find some more complex monthly mean tasks as well, which then use GeoVectorize from Numba and CUDA to get things done in case you're interested. Let's see how far we can get today. So what this basically does is it takes a very large 20 meters resolution Sentinel-1 image and blurs it. So it creates a Gauss kernel, and then it uses good old SciPy. SciPy? Do I use? No, I do my own thing. Yeah, because I wanted to have a fair comparison, so I did actually a Numba implementation on CPU, which uses all my 16 cores and actually convolves the Gaussian filter across the image and produces a blurred image. So this is the input image. Look, this looks like I don't have two windows. No. Right. Well, this is a high resolution Sentinel-1 image. And we'll see how many rows it actually has. It should be around 15,000, or it is 15,000 pixels by 15,000 pixels, so quite a lot. And let's have a look how well it performs. And for this, I'm going to use PyResample, which is a sampling profiler for Python, which is different to the deterministic profile, C profile that Python comes with. Well, it just as it has less overhead, which is usually not a problem for Python because Python usually doesn't do high performance code. But since we're dabbling now with Numba and CUDA, we are actually doing high performance code. And the advantage of PySpy is that it can also look into the non-Python code. So it is actually already installed, and the way to run it, and there's also a link in the presentation of the actual repo, is kind of, you then started with PySpy record, you specify the format. It can do flame graphs, so I can do this nice speed scope that I showed in the presentation format, and where you want it. And then you start your program or your script with the input that you want and with all the other parameters. So I'm going to run this quickly. And usually what I also like to do is do some old-fashioned edge top. You know, it's always a good idea to look at your edge top while you're doing things. And yeah, I see nice saturation of all my 16 cores. RAM is also behaving well. No peaks, no garbage collector things going on. Hopefully. So usually I do this is at least how I work. Combination of old school tools and new stuff. And we see now blurring took 27 seconds. Now, one asks, why is it not finished? Well, it has to store a giant image. It's an inherently serial process, and it also takes a while. So now I can open this in speed scope. Which is, you can also just Google speed scope, and it's also mentioned in the PySpy thing. And now I can drop in into my profiler. This is the order of time I see it. Like here we load the raster, and here we store the raster again. And most of the time is spent in Colmolf 2D, which spends most of its time. This is where it compiles the number code, and the rest of the time it's within the number code apparently. So yeah, doesn't get much more efficient than that. If I would have to process multiple images in a stack, I can try to stream the data, like interleave this loading and the saving. But as far as this goes, this is separated on the CPU. So the only thing I can try now is use a different hardware tool, which brings me neatly along to the GPU. So we decided now, okay, I want to see how this works on the GPU. And to first get started and a little bit acquainted with CUDA, let's do first. I also, by the way, this uses some proof tests because I talked about code habitability. So we are in luck that this code is already well tested, so we can make our CUDA changes confidently and without too much fuss, hopefully, if I did my job right. And we are just misuse this testing file now for a little hello world, just to get our feet wet with CUDA. So what I want to do is I want to implement a simple add function CUDA, so we all get to know the number. So we're going to use number has a more or less one-to-one mapping from CUDA to Python. And we're gonna exploit this today, so we don't have to write CUDA code ourselves. You can, of course, write CUDA code yourselves as well. It's not that hard. You can wrap your CUDA code into a C RT and then call this from within Python quite easily. But in the sense of maintainability, and if I can get away with Numba on an easy task, I would usually use Numba because for people who don't know C that well, or if I don't feel like I want to create a CI where I need to compile the library for each of my target deployments myself, sometimes it's easier. So, oh no, this is a German keyboard. Oh, well. So what I want to do is I want to quickly add to create a vector with side 3 filled with clues, vector B filled with 3s. Then I call in the vec function and this should be full. Well, this is my test, and it fails because it doesn't compile. Get here my B. Let's do this as well. And it returns again unpaired. Good. What would be the simplest thing for this to pass? Doesn't pass, hopefully. Perfect. Why does it not pass? Ah, yeah. Super. Perfect. So it doesn't pass because 2 is not 5. Excellent. So to see, get this thing to pass for now and see that this is actually working and the test is working before we do any performance improvements. Let's finish this very complex implementation. Yeah, everything's green. Perfect. By the way, just shout or tell me if there's something unclear or why I'm doing this test-driven development and or why if I'm getting too fast or too slow, let me know. So now we want to do this on CUDA. So to do this with CUDA, we have to create a, because it can't do return values that easily. Now we can give it A, B, and an out value, C. And how we do this is we have to somehow create the out value. Then add them together. Then we want to return the out. And this is actually called usually a kernel in CUDA windows. Now let's call this kernel as well. CUDA, that does all our CUDA magic. So first thing to know is first we need to from Numba import CUDA. Now we are in the CUDA world. Here, these NumPy arrays still reside on on our CPU RAM, so we have to transfer them to the device, which we do with this number function. And now those are device arrays. And of course, the output needs also to be on the device. So we call a CUDA device array, this shape with a data type equal to this. So, and to actually tell this thing that it should compile to CUDA code, tell this. Yeah. So this is CUDA code now. And yeah, and one thing I've forgotten, this is still on the GPU. Now we have to retrieve it from the GPU and put it back on the CPU so we can continue working with it. So now I've talked before about these blocks and streaming blocks and everything. So actually we have to distribute these calculations across threads and across blocks. I mean here it is actually quite simple because we only have a length of 3, so it's we can usually how you tell CUDA how many how many blocks and how many threads you need. So this would be, we just need one block because everything fits into one block, because we could have 512 threads per block and we only need 3 because the size of our array is 3. So now we can do in here, write our CUDA code. So this is not distributed. So we have this vector of size 3, and now we spawn one thread for each element in this vector. So the way now we can access this is we ask now the CUDA thread index X. This is, well, you can have 3D grids of threads and blocks because it comes from computer vision and graphics programming, where you usually deal with textures and volumes and things like that. This is why you have this concept X, Y, and Z. But in our case, we only have vectors, so there's only makes sense to use the X index, and we are only using this 1x3 thread block, which is very simple. That's it, hopefully. Let's see what I've forgotten. No, I haven't forgotten anything. So this now ran on the GPU device, on the CPU device. Of course, it's not very interesting because, again, context matters. This is way too small to be sensible for high throughput. So let's look at a more complicated example, to our Gaussian blur. So we want to improve now our Gaussian blur. So we have here this blur function, which takes a while. So we have here some smaller test data, but let's see how this actually does by clocking it as well. So we create the performance clock, which is part of some of the packages that are used in here. Whoop. Then I want on. Right. 0.7 seconds. Let's see if we can do better, even on the small set. I actually don't know because I haven't tried, to be honest, but it does work a lot better on the large one. So here in the convolve 2D, that's actually the thing we need to change. So we do something, create an, you see already, this looks already familiar because we're using Numba. So what I could do is, I say, script. Input this thing. And then we want to create a CUDA kernel instead. So now we have to think a bit more carefully about how do we distribute the block size. So usually how this works is you first define how many thread blocks you want. Usually a good first start is 16 by 16 thread block. This is kind of, if you look at tutorials or the official guides, it's usually what they want or what they recommend to start out with. And of course, I already have done CUDA implementation beforehand, so I'm gonna cheat a bit and gonna steal, because we're on out of time, can steal a bit from this function and talk about it instead. So the way this works is now, okay, as I said before, you can have even a volume. You can also have a 2D grid of threads. So I tell this function, okay, this is the total shape I have, and I want 16 by 16 threads. And this gives me then the blocks. This is very simple. I just get the shape, and then of course I round up, because I don't care if I maybe go off a bit, because it gets truncated later on anyways at the border. So how many I want, there are 16 blocks, and my image is 15,000 pixels long. That means I need that many blocks per grid. And those you define first this huge amount of blocks with threads in it, and they then get piped and streamed in parallel fashion, because each block is supposed to work independently and not communicate with each other. Each block will look around its pixel, do the Gaussian filter, low pass filter, or the Gaussian filter, sorry, and do all the work. And then it will fetch the next, as soon as a processing unit on the GPU is ready, it will fetch the next block and the next block. So you have a really large block grid, and here they defined how many threads you want to use per block. Of course, this always informs how many threads you need is also kind of determined by what algorithms you have. So here, actually, I could put this in constant, which is the case in the actual code. I'm not going to do this right now, I just want to get this to work. So here, instead of the number one, we want to create a CUDA JIT, and this is simply not true anymore. Yeah, that is still true. So now we actually have to index the correct threads. Also, we need to worry about the blocks, because it's not, there are like this many to do the calculation. So we have 15,000 divided by 15. So we have 938 blocks in each dimension defined, and down we need to figure out, okay, which pixel should this thread I'm currently in look at. And to do this, we usually go here. This is the x coordinate. X coordinate is then the block index, which block index in times x times the CUDA dim x plus CUDA index x. And x and y are the same thing, and I'm really running out of time, so I'm just going to copy this here again. So you see this very simple, doesn't change that much. As opposed to the code before. So now we know which pixel I'm in. Then within this pixel, I just look around the kernel radius, and this is simple, a kernel average sum. This is a Gauss kernel or any kernel basically. You create the sum around it and write it in the out value. That's that. So far, so good. Of course, we also need to do a little bit of fitting here, thing to the device. This one's already at the device, but it needs to get to the host again. So now we see if this is still working, and is it any faster? It is still working, and it is wow, double the speed, not bad. All right, let's have a look how much better we are with the big thing. So we do here we use the NSYS profiler, which comes with the CUDA tools. You can find online how to install it. Those who do not know can stay later on, but I'm really running out of time. So for those who can't stay that long, I'm gonna quickly finish up. And here we use the profile, and we start again, tells you where to write your output file. And then it calls Gauss blur. So you need to actually I don't. Let's have a look again. CPU is not doing much, but the NVIDIA SMI was briefly up, but the blurring took 6 seconds as opposed to the half minute it did before. So I would say that's a substantial gain. And for those who are interested, you can have a look how the profile of NVIDIA looks like and what's in there. I'm going to quickly wrap up for everyone else who is not that much interested in that, and open to questions then at the end as well. So now where can you go from here? Of course, I talked a lot about streaming and how cheap the GPU itself utilizes streaming to get this high performance. Of course, you can also stream the CPU RAM to the GPU RAM, and this is actually what's recommended, and CUDA already comes with tooling and with native support for those kind of streams. And there is things like on the CUDA, on the GPU, where I said branching is not that well liked. You can do some clever tricks by distributing different branches across the warp, so doing your speculative execution that the CPU tests manually, so to speak, or use the step function trick, which we used especially in computer graphics, where you just clamp it down to 0 and 1 and use multiplication with 0 and 1s instead of ifs. Of course, there are specialized intrinsic functions that work much faster, which have special hardware implementations that you can use. You find them on the CUDA documentation. You can also look into using halves, which are well supported in CUDA and on CUDA devices, because they are very popular for machine learning tasks. And you can now also look into the wider CUDA ecosystem, because there are many libraries and frameworks that solve many open problems already, like there's one for linear equation solvers, and even I think there's also now one that does nonlinear ones. I don't know if it's from CUDA or from someone else. But yeah, there's a huge ecosystem. And here's all the links I've promised. Are there any questions?
Hey, Bernhard, thanks for the nice presentation. It was, for me, the right level, so I say good job.
Thank you, I'm glad to hear that.
Also, a question, I know that you are working on some Earth observation related GPU processing, and I'm also in that field. Are there any specific Earth observation resources or libraries that are being maintained by some open source community that I could also look at for inspiration?
Honestly, that's the thing. I haven't found any, like, you mean now GPU specific?
Yeah. Or like, I know that this Numba is like a very popular for arrays, and you have then the X-array stack with all these tools. But I think, of course, there are like routines that are very common with Earth observation that would be implemented in, for example, this GPU Numba combination.
I've been looking for this myself, to be honest, and I haven't found much so far. Maybe I haven't looked that close yet. I've seen some where you use this they just use this jigs or JAX graphing libraries, but they're also usually very machine learning oriented. But the US found a trust region reflectance implementation that does it on a per pixel level, which is interesting. I've recently seen this done on the GPU, which is not really related to Earth observation per se, but used a lot, at least in my field. So that might be useful. Other than that, I mean, the task is very popular.
Yeah, of course.
And very good integration with CUDA, like you can now has a very integration with the machine learning side of things, but I also looked into that a bit, how they actually handle CUDA devices, and usually, well, how I've used task in combination with CUDA so far is just to use task as the scheduling and streaming thing that does all the, streams out the huge chunks from my data cube and then send it to the GPU and do the processing there. But I haven't found any open source library that, for instance, I haven't found a resampling library so far that works on a GPU. I think resampling would probably be well suited, at least for high resolution data, not maybe the creation of the lookup table, but once the distance matrix is there, might actually work quite nicely, but it's a bit more complicated to implement this thing on a GPU. But yeah, other than that, yeah, monthly means there is an example in the repository, code repository, you can have a look at. If you already use from Numba GeoVectorize, you can change the target to CUDA, and if you have all the CUDA libraries and CUDA toolkits installed, then it will just work out of it works then on the GPU. If it's then more performant, depends again on your context and how long does it take to stream the data onto the GPU. But unfortunately, I don't have any other open source specific Earth observation CUDA related open source projects. If anyone knows anything, I'll be glad to hear as well.
Yeah, I was recently looking into GDAL's support for CUDA as well, and as you mentioned, resampling. I think it might just be the can't remember exactly which interpolation method it is. It might be bicubic, but from what I've seen, yeah, I think you can maybe do bicubic interpolation with GDAL, but that needs GDAL recompiled with CUDA support, which is another thing to dig into. So yeah, from what I saw, it's not simple, but it's possibly worth looking into.
Well, I didn't actually know that CUDA was going that direction. It's good to know. I actually haven't completely forgot about looking into it, because so far I was always using Array and X-Array and hiding the CUDA stuff behind other libraries. Yeah, thanks. Gonna have a look.
All right, thanks.
Any other questions, or does anyone want to have a look at the CUDA profiler from the answers that are shown at the end, just how it looks and how to start it, or is everyone...
if you have time, yeah, that'd be great, please.
Yeah,
sure. That's why we are here. Just quickly, shouldn't take too long, famous last words. It says, so you can, this comes with the pre-installed, if you, no, you can't install this really conveniently with your package management system like up. You have to sign, well, there is something online, but you have to sign up at the NVIDIA homepage and get the developer access, which is free. And then you can download the thing yourself and install it, and that actually works. The one from up never really worked for me, just as a side note. Yeah, so this actually, it looks the same as the, so it's going to be quite quick. Looks the same as the works the same as the PySpy profiler. Kind of, you know, you see here a little bit how the memory management is used. So this is hidden behind Numba. Actually haven't found out yet why QMem3 is happening one core through the whole process, but maybe this mystery will be solved at some point. And you can zoom in and you can have a look what's actually happening there. I think this is the, yeah, here we copy, this is where the magic happens, from copying data from the CPU RAM to the device RAM. So then there's not much happening. I'm guessing this is where the this is where it compiles those things. Usually it doesn't look like this. Well, sometimes it does. And you can have a look at what is actually happening on the device on a very high level. And here again, you see, okay, this is my workhorse algorithm. Here you see what are my kernels doing, and most of my kernels are spending time in the Gaussian blur to the CUDA kernel, which makes a lot of sense that they're there. So this profiler again is really nice if you kind of want to, if you want to debug or profile how is my memory alignment and how much time do I spend copying, like here I copy back from the device to the host. Not so specifically what does the CUDA kernel itself do. There it's ANSYS compute, but that's a highly different beast and probably too much for a beginner's introduction, because at start, like for most problems, at least in Earth observation, the algorithms aren't that complex. So usually they are just like this. You have a thing, you have a thing, pixel, you look around or you do something up, monthly means on a per pixel basis, or transforming decibel to linears. So if you're doing more complex things where I would need the other profiler from NVIDIA you find online, you're already at the advanced level, I would say. Like for instance, here I can quickly show you how you can do this GU vectorize. So this is how I do an iterative monthly mean with CUDA. So I create this geovectorize function, which takes a source and a new observation and adds it actually into the distance, because there is an issue open at NumPy that you can't easily add without add into and do an in-place increment of an array, which is why I still need this unused destination parameter. And so here you also see the conversion from decibel to linear units, and you can just change the target to CUDA. This is how the thing looks in CPU version, just says parallel, and that's and here I do have a destination. Yeah, that's it. Any more questions?
It was really, really valuable. Thank you so much.
Thanks, Claire.
Thanks also from my side. Perfect.
My pleasure.
Yeah, thank you very much as well from me. So that's everything. We'll stop the recording now, and the recording will be uploaded to YouTube, and I'll share it with you after the meeting.